Hi everyone, this is day 6, coils for the Sniffer. As I said, I'd come back to this, and today I sat down and did a few calculations. There's a little used calculator on my website called the VFO Helper. The VFO Helper allows you to compute component values for typical LC VFOs. I'll add a link to it in the description for this video, but one of the things that it is useful for is if you happen to know the tuning range of your polyvaricon. If we go back to, this is day 4, the RF Sniffer. This capacitor here is a plastic polyvaricon capacitor. It has two gangs. You put both gangs together and you get a tuning range of about 12.4 picofarads to about 213, so about 200 picofarads of tuning, but with an offset of minimum capacitance of about 12 and a bit picofarads. So if you put these numbers into the calculator and you start trialing some different inductances, you can work out ranges for what inductor you'd like to put in here for whatever frequency range you'd like to cover. So I did that a bit, and I played with the calculator and got some figures that I could start with, but the devil is always in the details. Practical inductors have this parasitic parallel capacitance across them, and this adds up with this minimum capacitance here and means that the maximum frequency that you're likely to see, if you pick any value of inductor here and you do the maths, you'll find that these ranges, these are practical ranges which I measured using my signal generator. I'll show you how in a minute. So this is a 2.5 millihenry inductor. It tunes from 237 kilohertz to 647 kilohertz. Now, the upper range here is very much limited by this parallel capacitance, not only by the actual tuning capacitance, so the minimum tuning capacitance. So I did the same thing for a whole bunch of inductors, and as you can see here, there's quite a range. And I've put an asterisk next to the ones that I selected to actually use for practical overlapping ranges. So 6 of them covers LF and HF, so from 237 kilohertz to 38.3 megahertz. And here they are. I made this little jig here for the exercise. It's just a piece of IC socket soldered to a connector, so I could plug in the chokes. These are just commercial ferrite chokes. I think they're made by Philips. They're quite old now. They might actually be hard to get, but you can certainly get similar molded inductors, anything that's got like a little ferrite core. The only problem with having the ferrite core is that if you are probing a circuit that's a tuned circuit, getting the ferrite near it will pull the circuit. So you might want to make up a set of coils also that uses just copper wire and no core at all. That means you'll need obviously more turns, and it'll be physically larger for the same amount of inductance, but it'll be less likely to pull the circuit. But the ferrite ones couple very well, and it's useful to have both sets actually if you can. What I haven't done yet is actually put a decal on here with calibrations for each of the 6 coils. But it's really an exercise of sitting down with the signal generator. As you can see here, I've got the signal generator plugged into the frequency counter. It's about 12.3 megahertz at the moment that it's generating. It's coming out to a little coupling loop of wire here, and you can see if I bring the dipper here near it. So with this lash up, you can sit down and compute the ranges. Obviously you can rack the capacitor all the way up to its minimum capacitance and then all the way down to its maximum capacitance. That gives you the 2 ranges. You can set specific frequencies of interest, like amateur bands or 10 megahertz, 5 megahertz, even multiples, whatever your taste may be. And then you just twist the capacitor around till you get maximum frequency on the piezo, and then you mark the dial. So that the actual exercise of calibrating it is not particularly difficult. It's just a little time consuming. The other alternative, of course, if you're making coils, particularly if you're winding your own, is if you have day 5's project here. The inductance meter is quite helpful. While you can use the standard equations, which again I'll talk more about in the article when I write it up, it's very handy to actually be able to measure the inductance of the device when you've finished it, to see that you're in the right ballpark, and just to really double check your work. It's also useful for measuring additional capacitances. If you wanted to, you could put capacitors across these in the actual finished plug-in device if you wanted to limit their range. Could be handy if you wanted to cover one band with high resolution. One option, if you're actually building this device from scratch, is to, instead of permanently attaching the capacitor here, with a switch, you could bring it out to an additional contact on the coil, and that would allow you to put a series capacitor in series with it, in addition to, say, another parallel capacitor, and limit the amount of effective capacitance that the LC circuit sees. And this would allow you to, make very narrow tuning ranges if you wanted to. Of course, the Q of the capacitor, the Q of the entire tuned circuit is not going to be particularly high, so maybe you'll get a few percent bandwidth if you're really lucky and you use very weak coupling, but still could be useful. And the general principle can be applied to making variable frequency oscillators for various other projects. For example, if you want to make a local oscillator for a receiver that tuned, say, one band, a couple of hundred kilohertz, you go about it in much the same way. And the calculator that I spoke about at the start of the video is especially useful for that, because you can compute the band set and band spread capacitances that you would need given a specific inductor and a frequency range of choice. Unfortunately, the calculator is one of my older ones. It doesn't yet take multipliers, and you have to put everything in scientific notation. I might invest a little bit of time in a few days to turn it into one of my new format calculators that has much better validation and just general usability. But as long as you just put in, for example, 1 microhenry would be 1e minus 6 instead of just 1u like you would put in the modern calculators, and the output's a little bit more terse. But it does the job, and it's quite a useful little calculator. This is, of course, the standard equation that you can use for calculating all of these. Just plug in the numbers for the upper and lower capacitance in here and solve for L, or with a known L, like one of these standard preferred values, you can get out the frequency range. And that's really what the calculator does, but the calculator offers a few other possibilities. It can solve for either term, depending on which one you put in, including the capacitances, and it does the ranges and all of that, and it can find the capacitances for you that you'd need to set a specific range. Alrighty, that's it for day 6. This is just going to be a quick one, more waffle than actual circuit, except here we have actually done some real practical work. Tomorrow, I think optical, as I mentioned in my last video. Been wanting to play with optical for a while. Oh, might as well take this opportunity to catch up as well. This is the audio amplifier from day 2. I built it onto a little piece of circuit board so that we can use it for other projects. And that is the power supply from day 1. Well, pieces of it anyway. It's not quite finished yet. I've got it calibrated as well, but I just thought I'd build it rough and ready on a piece of cardboard. Again, it's going to be useful for other projects. Alrighty, until tomorrow. Bye.